Yes, so begin. Today is my last lecture, and I have no more opportunities to postpone something to the next time or anything. Something will remain, which is covered by my notes, and will not be properly done today. I hope you may wish to look through it. But my purpose today is to discuss one very much relevant example of the calculation of the de Rham cohomology. And I will do this for the sphere, Sn. Actually, this computation, why I prefer to present it here, this computation uses everything we ever considered regarding differential forms, integrals, differentials, whatever. Besides important geometric result concerning spheres, we will have an opportunity to practice in all this material. So, the shortest statement of the result which I'm going to present today is the following. The de Rham cohomology of the sphere Sn, n is an arbitrary number, arbitrary positive integer. The dimension of this, because this is a vector space, is 1 if q is 0 or n, and 0 otherwise. Now, if you consider the definition of the de Rham cohomology, you remember HQ de Rham of M is a quotient of the space of closed Q forms. Q form is an abbreviation meaning forms of degree Q on M factorized bar exact Q forms on M. So 0 means that these spaces are the same, which means in particular, which means in turn that every closed form is exact. So this statement means that if Q is not 0 or n, then every closed Q form on Sn is exact. As to the cases when Q is 0 or n, something else can be said. First, if Q is 0, in this case, the sphere is not very much different from other manifolds, because a 0 form is a function. A closed zero form, it is a function whose differential is 0, which means, roughly speaking, that it is constant, or more precisely, it's constant on every component. Sometimes people say, just to be looking more smart, locally constant. So is a constant on every component function. And exact is 0. No forms of degree -1. So no differentials. Usually we attribute to the 0 form all possible degrees. So 0 is a form of whatever degree you wish, and the only exact 0 form is 0. After which it is clear that the dimension the RAM cohomology of any M is the number of components. This is a universal fact which is true for any manifold, in particular for the sphere, and in the case of the sphere which is connected. We will have that H0 of Sn is just the ground field. R is R in our theory. The case of forms of degree n is slightly different, because forms, well, first of all, on an n-dimensional manifold, for an n-dimensional manifold, well, it can be M. Absolutely all n forms are closed. No choice, because no forms of degree n plus 1. Now, if your manifold is exact, if your manifold is compact and oriented, you can say orientable, then, well, oriented, then forms have integrals over the whole manifold. And exact forms, the integral of exact forms, as we know from the previous theory, from the Stokes formula, the integral of any exact form is 0 over the manifold. I mean manifold without boundary. Closed manifold, compact manifold, compact oriented manifold without boundary. So the integral of an exact form is 0. But actually, for an arbitrary, connected, compact, oriented manifold without boundary, the form of degree n is exact if and only if its integral is 0. This fact is more deep. Well, in one direction we know it, that the integral of the exact form is 0. But if the integral is 0, then the form is exact. This requires some proof. The proof is contained in my notes. I will not discuss it today. But for the sphere, it definitely means that this dimension 1 used to be here. Dimension 1 of the cohomology Hn comes from the integral. Every n form on Sn has an integral. So we have a map of the space of all forms, all closed forms, because they're all closed, into R, the integration. And actually exact forms form precisely the kernel of this map. So for the sphere, this means that Hn diram of Sn has dimension 1. And as I said, and I will not prove this, the same is true for any what? For any connected, compact, oriented manifold without boundary. Compact, without boundary, closed. Again, this fact, a proof is contained in my notes, so you can look through it. It is interesting. But today I will consider the case of the sphere. So I will prove everything for the sphere. Also, I will use a theory which was formulated last time. The proof is very short. It is contained again in my notes, but I prefer, at least not immediately, I prefer not to consider the full proof. And this fact is the homotopy invariance. So if two smooth maps between two manifolds of any kind are homotopy, then the induced homomorphisms in the opposite direction of the de Rham cohomology of any degree are the same. The proof is short and very much algebraic, and actually it may be even more reasonable to consider it not in this context, because nothing in this proof actually requires this setting, manifolds and so on. It's algebraic proof. Well, so I will not prove it, but I will use it. And let me immediately say what precisely of the homotopy invariance I will use in the proof of this theorem before I prove anything. The first thing I mentioned last time, this is Poincaré lemma. We compare two manifolds, Rn and a point. And using the homotopy invariance, we prove that these two manifolds have the same de Rham cohomology. The de Rham cohomology of a point is nonsense. Just H0 has a dimension of 1, and everything else has to be 0. Then the same holds for for Rn. And this fact is maybe formulated without cohomology. It means that if you have in Rn a form of any positive degree, which is closed, then it is exact. And those of you who are involved in teaching calculus know that such things are considered in the elementary calculus course. That you have, they say a vector field, but actually you have a form, differential form, and you want to find the degree 1, and you want to find the potential function. Potential function is, in our language, is a function form of degree 0, of which our one form is differential. And for this, certainly there is a condition that this one form should be closed. And you know then, some geometric language, that you need to require something else to find how to say univalent potential function. I mentioned simply to establish a bridge between things which you know very well and things which may be new for you, although I'm not sure of that. So Poincaré lemma is one fact, but I will need to use another fact, also following from the homotopy invariance of the de Rham cohomology. Let me show a picture to you. So, as you know, as I already said, we will consider a sphere. This is a sphere. A sphere dimension n. Then it has the following thing, equator, which is Sn minus 1. This is the last coordinate, z in space, or xn in n-dimensional space. And also, I will consider this equatorial belt. You understand, I consider two planes parallel to the plane of first and one coordinates. They intersect the sphere, and between them we have this layer, equatorial belt. Let me denote it for the moment as B. It will have another notation, but B is belt. And then I want to say this is open. I do not include the It is not important, but I prefer to use this language. B is open, doesn't include the boundary spheres. And then the de Rham cohomology of B is the same as the de Rham cohomology of Sn minus 1. This is why. Look at this B. And there is a very obvious projection. This B can be collapsed on the equator. So every point is moving along the meridian. This is a map of Sn minus 1 into B. I can denote it well. You remember this map. And also there is an inclusion map of B. No, this is the map of B and Sn minus 1, and also there is inclusion, Sn minus 1 into B. There are two maps and two compositions. This composition is the identity, because we first embed the sphere into the belt, and then project the belt back into the sphere, but every point of the sphere is mapped onto itself. The second map is not the identity. So we take a point of B, it is mapped onto a point of Sn minus 1 by map projection, and this point of Sn minus 1 is considered again as a point of B. This is such a collapsing of map of B into itself, which is very obviously homotopic to the identity. But it's not the identity, it's such a collapsing. Now, if we apply all these maps, we take all these maps and take the corresponding induced homomorphisms of the de Rham cohomology, let me write it. So I have these two, as people say, diagrams. And there are induced de Rham cohomology maps. Then everything here. This is the identity. This is the identity. And this is the identity. Which certainly means that the two maps between the groups HQ de Rham are inverse to each other, so the spaces are isomorphic, the same dimension, the same everything. Okay? This is precisely the second property of the second corollary of homotopy invariance, which I am going to use today. So actually, homotopy invariance for us for today is concentrated in these two facts. First, Poincare lemma, and second, this. This belt, equatorial belt, and the equator have the same de Rham cohomology. Now my theorem again. What remains, I will use this picture again, but still I prefer to erase it now. So my theorem, formulated not in the language of the de Rham cohomology, but rather in the language of differential forms. Suppose that alpha be a differential Q form on the sphere which is closed. The alpha is equal to 0. I suppose this Q, I don't consider the case of 0 because everything clearly is the case, but Q between 0 and n. And additionally, I want to suppose that if Q is equal to n, so this assumption means nothing if Q is not equal to n, then the integral over Sn alpha is 0. Here I have all the assumptions of the theorem. And this should imply that alpha is exact. So a closed form of a positive degree, which additionally has 0 integral over Sn if its degree is equal to n, is exact. And this is precisely my theorem, which I'm going to prove now. My proof will be very direct. I will take this alpha and just construct a form beta such that alpha is equal to d beta. I will also be using induction with respect to n. But this is the theorem. Questions at this moment? Doug? Henry? Joe? No questions. So, induction. Certainly, in reality, this induction is should begin with the case of the zero-dimensional sphere. But this case is not very convenient because the statement will be slightly different, even for q equal to 0. 0 and n merge. So I prefer to do some extra work and to prove this theorem separately in the case when n is 1. In which case, actually, this is very easy. It is one of the exercises in my set of exercises, and actually one of you did this exercise. But anyhow, so I begin with the case when n is 1. S1, if we don't know, is a circle. Q between 0 and n and not 0, then Q is 1. So we have one form, alpha, omega 1 over S1. It is closed. Now, what is the one form on omega 1 S1, on S1? Actually, there exists a form d theta. Theta is the angular parameter. It is not precisely a function on S1 because it's multivariate. Still, d theta, it's very clear. There is this vector field, say, of vectors of certain length, say 1, directed counterclockwise tangent to the circle, and d theta is just the differential form which takes value 1 on this field. Now, an arbitrary form, alpha, in terms of analysis can be written as f of alpha d alpha, but theta is not a function. It is more convenient to consider alpha to write f of x dx, where f is a periodic function with period 2 pi. Well, period is your choice, depends on the radius. So, a differential one form on the circle can be regarded as the expression, whatever it means, f of x times dx, where f of x is a periodic function with period 2 pi. A zero form, that's a function, is simply a periodic function without dx. So this function f of x is periodic. And we want to know whether, we forget about our conditions, just want to know whether this form is exact. It's closed, but exactness. To be exact, we need to consider the function g of x. Let me write, well, g of x, integral from 0 to x, f of GDT, right? The integral of f. Is this integral periodic? The answer is not always, because to be periodic, g is 2 pi periodic if and only if the integral from 0 to pi is 0. This integral from 0 to 2 pi is the same as the integral from alpha over the circle. If this is not true, then simply the function g of g will have different values as 0 and 2 pi. If it is true, then it will be periodic, obviously. It will have equal values at x and x plus 2 pi always. And if so, then we have a full answer to our question. This form f of x dx is the differential periodic function. That is, alpha is exact if and only if the integral of alpha over the circle is equal to 0, precisely our statement. So the case when n is 1, well, certainly, if you want me to be boringly rigorous, I can say that there are forms with non-zero integral. So this map on the R is onto, obviously. Now we suppose, so the induction begins at this moment, and we assume that the theorem, which I'm proving, holds for a sphere, so n now is some number greater than 1, and we assume that the theorem holds for Sn minus 1. And using that, I want to prove that it holds for Sn, which will give us the desirable result. So I begin proving my theorem, and I will need a picture, not so much a picture, but I need to have notations. So this is Sn. This is the equator, Sn minus 1. Now, I consider two sections, and this, the open set, not including this, will be U1. This is Sn minus 1. This will be U2. That's a covering, open covering over Sn. Also, at some moment, I will need the upper hemisphere dn plus and the lower hemisphere dn minus. I think that now this picture contains all notations all notations regarding the sphere. There will be forms, alpha, beta, gamma, but the geometric notations are all on this picture. I will try my best not to erase it. But I will erase the statement because even if you don't remember it, we will use it. So let alpha be a form with all our conditions. So the alpha is 0, and if q is n, then alpha has 0 integral. I consider the restrictions of alpha to U1 and U2. Remember, U1 and U2 are two open sets. These open sets are very much homeomorphic, diffeomorphic, whatever you wish, to the open balls, to the Euclidean space, right? By this reason, I can apply to them the Poincare lemma and write that this is equal to d beta 1, d beta 2, where beta 1 and beta 2 omega q minus 1 of d2. Now, the difference, beta 2 minus beta 1, is defined where both forms are defined. So this is a form of degree q minus 1 in the intersection of u1 and u2. The intersection is visible there. It was denoted as b before. What do you think of the differential of this form? The differential of beta 1 is alpha, where it is defined. The differential of beta 2 is alpha, where it is defined. The difference alpha minus alpha is 0. I don't think you will have serious objections. So this form is closed, right? We have a closed form on this intersection. Now I say something irresponsible, and then we will make corrections. Actually, this set u1 intersection u2, b in our previous notations, is, from the point of view of the Ram cohomology, the same as the sphere of Sn minus 1. And we have our induction hypothesis. So this induction hypothesis, roughly, means that this form beta 2 minus beta 1 is exact. Beta 2 minus beta 1 is exact where it is defined. Why I say roughly? Because there are additional conditions, which I disregard now, but I don't want to disregard it at the next moment. It is true if the degree of this form, q minus 1, is not lies between, it definitely lies between 0 and n minus 1, because q is between 1 and n. But also there are some, there should be some additional arguments in the boundary cases when q minus 1 is 0 or n minus 1. So if q is not 1 or n, then beta 2 minus beta 1 is exact. Now I need some additional arguments in the case when q is 1 and q is 1 and q is n. Q is 1 is a stupid case. You see, in this case, q minus 1 is 0, believe it or not. What is, so this closed form is an alpha 0 of this, and this is simply a constant function. Omega 0 is a function, closed constant function. So this is actually some constant c, and then just replace beta 1 by beta 1 plus c. Beta 1 was defined from this equation. Certainly, if you add a constant function, if beta 1 is a function, and you add a constant function to beta 1, then it will not affect its differential in any way. So we can replace beta 1 by beta 1 plus c. C is a constant. And as soon as we do this, beta 2 minus beta 1 becomes 0, and I personally do not know form more exact than 0. So this case is okay. The second case, when q is n, is very slightly, requires some work. I think I can erase this, you remember that. I prefer to keep the picture. So, if q is n, like q minus 1 is n minus 1, then to state that the form is exact, we need to know that its integral is 0 over n minus 1. And I say that this is so. Why? This is because, let me Consider this picture again. The integral of beta 1 over Sn minus 1 is the same as the integral. This is the Stokes theorem, right? The integral beta 2 is the same than minus. Take the difference. And you will have that the integral over Sn minus 1 of beta 2 minus beta 1, I should take the difference in that direction, is the same as the integral over dn plus minus the integral of dn minus of alpha, actually. This is alpha, both. And this integral of alpha over the upper hemisphere and minus the lower here is the same as the integral over the whole sphere, because this in the sphere dn plus appears with the same orientation as in this picture, and on the lower sphere is the opposite orientation. So this is precisely the integral over Sn alpha, which is 0. So we see that the form beta 2 minus beta 1 has 0 integral if its degree is n minus 1. And hence, again, it is exact according to our induction hypothesis. So, always exact. Exact, this means that it is a differential of some form. Very definitely. So beta 2 minus beta 1 is the gamma, where gamma is this. Q minus 2. You should realize that in principle Q could be 1. And 1 minus 2, as you may know, is negative 1. But in this case, beta 2 minus beta 1, according to our construction, is 0. And then this means precisely this, that 0 is differential of 0. If Q is 2 or more, then this is our result. We are close to the end, so please questions now. So we have this gamma. Now I want somehow to use this gamma. I want somehow to use this gamma to make the forms beta 1 and beta 2 agree on the belt, on the intersection of U1 and U2. If they agree, if actually beta 2 minus beta 1 is 0, then we have just one form beta on the whole manifold, on the whole sphere, whose differential is alpha, precisely what we need. If they disagree, we need to make some correction. And this is precisely what I'm going to do. So now I want to change the choice of beta 1 and beta 2 using this gamma in such a way that they will agree on the intersection. How to do this? I already said to you that in this proof we will use all we know. And now I want to consider the following thing. The partition of unity, which is subordinated to the covering U1, U2. So we have two functions, f1, f2. The sum 1 with supports containing in U1 and U2. Well, I don't expect any comments, but there is such a theorem. Then I do the following. Consider the form f1 times gamma. And my stupid question, where is it defined? Certainly gamma is defined on the intersection, U1 and U2. But the function f1, you know, is equal to 0 in the complement to u1. And actually, its support is within u1, so it is equal to 0 also in some neighborhood of the boundary, right? So actually, when we multiply gamma, which is defined only here, by f1, then it is naturally defined on the whole set u2. Simply be extended by 0 in this part, complement of u1, yes, this set. And the whole set u2. Here, my form is f1 times gamma, and here my form is 0. And they agree on the boundary because the support of f1. So this form actually and similarly now my last action. I want to change my choice of beta 1 and beta 2. How I can do it? Beta 1 and beta 2, we know only one thing about them. Its differentials are alpha within u1 and u2. So if you replace the form beta 1, for example, by some other form, and the differential stays the same, then it's allowed. How to achieve this? You can add to beta 1, subtract from beta 1, any form, which is exact, which is closed, but we prefer the exact forms can be given by formulas. So consider new beta 1 and new beta 2. Beta 1 prime is beta 1 minus the differential of this. This is in u1. So the differential also is a form in u1. All these forms are in omega q minus 1 of u1. Now take beta 2 prime in the same way. Maybe the sign somewhere is wrong, then I will correct it. Maybe one of these minus should be plus. Then, first of all, beta 1 prime, beta 2 prime still have the differential alpha, right? And now, beta 2 prime minus beta 1 prime should be beta 2 minus beta 1 plus the differential or minus the differential of f1 gamma plus f2 gamma. For this purpose, I need to have plus here, right? Yes. So correction, plus there. This is gamma because f1 plus f2 is 1. Right? And the gamma is precisely this. Where it is defined in u1 and in section u2. So this new difference, beta 2 minus beta 2 prime minus beta 1 prime, is 0 on the intersection. So again, beta 2 prime and beta 1 prime are not worse than the initial forms, beta 2 and beta 1, but they agree on the belt. And hence, they form, even I can erase the picture because I don't need it anymore. So beta 2 prime and beta 1 prime comprise a form beta prime on the whole sphere, and d beta prime is alpha, which is the end of the roof. Questions? So I used absolutely everything in my proof, but the proof is okay. If you don't have questions, since this is my last 3 minutes, I want to say something in addition. First, in this proof, how much was it really important that it is a sphere? If it is not a sphere, what actually we used? We used the fact that we have a manifold, a covering, U1 and U2 in my case, but it could be a covering of not by 2 sets, more. We have some information about the de Rham homology of the intersections of the elements of this covering. And from this we deduce the information of the de Rham homology of the whole manifold. This procedure, in principle, can be applied to any manifold. It is actually very common in mathematics that you have, and we already discussed this here in some examples. You have something, whatever it is, for elements of an open cover of some manifold or whatever. And then you want somehow to deduce from it, and also for the intersection. Maybe for, if there are more than 2 sets, for triple intersections, and so on. And in principle, you can try to obtain the information of whatever you wish for the whole manifold using this information, pieces of information for coverings and for covering sets and their intersections. If there are 2 sets, then those of you who are familiar with topology know that there exists such a thing as Meyer-Vietoris sequence, which actually does precisely what we want. More or less, certainly, my proof can be translated in that language. If there are more than 2 sets, then Meyer-Vietoris exact sequence doesn't exist anymore. There exists, if you wish, something like Meyer-Vietoris spectral sequence. But actually, this language, for those of you who appreciate it, is the language of Čech homology and hence of the shift theory. By this reason, actually, the true computation of the de Rham homology belongs to the shift theory. And it results in the de Rham theorem, which shows that actually the de Rham homology is not different from any other homology. This is one thing. Also, this is the last thing I want to say. If the manifold is not compact, then we can consider similar theory for compactly supported forms. And there will be compactly supported de Rham homology. My notes contain the computation of compactly supported de Rham homology for Euclidean space. It is important, but I have no time anymore to consider it here. It is in my notes. I appreciate if you read this, you can ask questions and whatever. With this, I finish. We all are grateful to Jennifer for the filming. And that's all. You have my final assignment.